this. Okay, so I got something from the chat. I was saying that I got a message from yes, insertion sort is easy. Merge sort, yes, merge sort. I would say a merge sort is I would say probably demand twice amount of the time of insertion sort. So how long does the insertion sort take from you? Okay, if you finish insertion sort within 3 hours, type 1. If it takes you more than from 3 to 5 hours, type 2. From anywhere from 3 to 5 hours, type 2. If it takes you more than 5 hours, just type in 3. So I just want to see how challenging it is for you. Okay, I say 6 once so far, and 7 and 2.5. Yes, 2.5 or so 2. Okay, so meaning that maybe one of us spend more than 3 hours on it. Okay, so 3. Okay, so more than, so I see one comment saying that 3, meaning that you spend over 5 hours on it. Okay, so if you spend over 5 hours on it, it means that I think the problem is mostly because of Java rather than your understanding of insertion sort. So it means it means that your Java programming basics are not as solid as it should be. So but I totally understand it, because so a lot of times so the understanding of a course or of a skill heavily depends on the instructor. So if your instructor does not teach well in your Java 1 or Java 2, or say you have some personal issues during that time, yes, this happens, but it is fine. Up until now, up until this class, you still have the opportunities to make it up. But I would say after this class, if your Java programming skill is not good, is still not very good. I mean, if you go to take the 300 level and 400 level classes, they will be much more challenging. And so even though say the really bad thing is that even though you finish your college with a CS or IT grade degree, so it's hard for you you find that you are not that good on the job market, then I would say this is the worst thing, rather than failing a couple of courses. So failing a couple of courses. So so my task is to avoid that, to help you to avoid that. Okay, so to give you some opportunities to make up the things that you should make up your Java program, not only make up but also improve. So I hope that at the end of this semester, so everyone is able to start to do the programming, to start a Java programming, small Java programming project by yourself without my skeleton code. So that's the objective. Okay, so so far we learned 2 sorting algorithms, named insertion sort and merge sort. So what are the complexities of them? So what is the complexity of insertion sort?
It's like n squared or something?
Yes, n squared. What about merge sort?
O(n) log n.
Yes, O and log n. Cool. So O and log n. So which one is faster in terms of the execution speed?
Merge is faster.
Okay. Merge is faster. Okay. And this one is going to be slower. Okay. Slower. But this is about execution. Okay. Execution speed. And then if we talk about implementation speed, meaning how long it will take you to implement that, guess which one is going to be faster and which one is going to be slower.
Insertion is faster.
Yes, insertion is faster. I mean, so probably, say if you spend 2 hours on insertion sort, probably you will spend 4 hours or 5 hours on merge. So I mean, this is pretty common, and it's almost this almost so this is actually it's kind of like very popular in a computer science world. So if you got an algorithm that is easier to implement, it usually means that it is slower in terms of the execution speed. But if we spend more time on just like typing the code, understanding the algorithm, and so that if the algorithm is more complicated or better designed, it means that we will need more time to implement that. But when you execute it, it's going to be much faster. So we're going to see this phenomenon continuously throughout the semester. So better things like in real life. Say if you want to, let me just still use cars as an example. So if you want to buy a Toyota, probably you will only need to save, let's say, 2 years. 2 years of so it's easier for you to get, but it's slower on the road, and it's not that fun on road. But if you want to go to buy a Porsche, I'm not sure if I spell Porsche correctly. So let's say if you want to buy a Porsche or BMW, so probably you will need to save 5 years for that, but it's much fun to drive. Okay, so more efforts means more enjoyment. Same here in the computer science world. If you put more efforts on the merge sort, on implementing the merge sort, you will see how fast it is compared with insertion sort. And after you see the difference of this performance, and you think, okay, so the additional amount of time that you spend on implementing merge sort totally pays it off, and it's a big. So I would say you will feel very excited after observing that. Okay, after you finish your homework too. So so far we learned these two insertion sorting algorithms, and today we're going to learn two more. So actually, so I'm just going to go over this slide very quickly. And in this slide is mainly talking about heap sort. It is a sorting algorithm, and that is very complicated. It is very complicated to implement that. Here you see 3 functions already. These 3 functions are relatively easy to implement. And besides those 3 easy functions, we got 3 more. So in total, to implement the heap sort algorithm, there are 6 functions for you to implement. And out of them, 3 are easy, 3 easy ones, and 2 are medium level, and 1 of them is really hard. So this one is really complicated to implement. So I'm not going to not only to implement that, but also to understand it. It takes a long time, and so I'm going to skip this sorting algorithm in our lecture and take it as an option for you. Okay, so if you want to learn this algorithm, feel free to go through these slides plus read this chapter, this sub chapter in the book. And so So the reason why I want to skip that is that it is just too hard for you to understand and implement. So in your job interviews, no one is going to check your understanding of this algorithm. So because it's in real world life, we don't usually. I mean, normally we don't implement that. We don't use this algorithm to sort an array or something, because we have better options. And better options meaning that less time to implement, and which is also faster in general. So this one is not that. So this algorithm is beautifully designed and complicatedly designed, but the practical value of this algorithm is relatively low. That's why I want to skip that and focus more on the other two sorting algorithms, named the Quicksort and the counting sort. This is our main task today. And let's talk about before that, before I step in, so here, okay. So what kind of design philosophy did we use in merge sort?
We split the array and then break it down into smaller pieces, individual, and then we resort it back.
Yes. Okay, so
basically.
Yes, there is a good name. There is a very cool name for that. We call it divide and conquer, right? And but what you first explain is absolutely correct. Divide and conquer. So in the divide and conquer, we have 3 steps, which are divide and conquer and combine. So I'm not sure if you still remember the example I gave you about moving a car from a junk car from the garage to a junkyard. So divide is to divide the big task into smaller pieces, and conquer is to tackle each task individually. Each is simple and subtask individually, and then combines to combine the solutions to the sub problems into a big solution to the whole problem. So this is the divide and conquer design philosophy. And today we are going to the first algorithm that we learned is also is named Quicksort. It is named Quicksort, and it also uses this design philosophy. So but the application of this philosophy is totally different from merge sort. So now I'm going to explain it in details with an example by drawing some chart. Okay, so here we all know that. So I mean, start from merge sort. So in merge sort, when we are giving a very long array, we divided. We said, okay, this is too difficult. So we divided it into 2 smaller subarrays of the same size, and then we further divided. Okay, so we keep dividing it until each subarray only includes 1 element. Okay, so this is the divide step. And so in the conquer step, we basically need to sort each of these subarrays. Okay, so if a subarray only includes 1 number, do we need to sort it?
No.
No. So if it only includes 1 number, basically there is no comparison. So naturally it is already sorted. The array is already sorted. So so here in the merge sort, in merge sort, we do nothing in the conquer step. And then in the combine step, we basically combine 2 consecutive and sorted subarrays into a longer sorted subarray. So this is what we do. We combine them 2 by 2, and we keep combining them until we reach the final solution. We get all the numbers included in a sorted array, and this is called the combine step. So we said that in merge sort, in which step did we perform most of the job?
Divide.
No.
Conquer.
No,
Combine.
conquer is basically nothing. We don't do anything. So we said that we do most of the job in the combine step. So this is where most of the job is done in the combine step, because in the divide step is pretty straightforward. We're just giving a very long array. We just need to find the middle point and divide it from there. In conquer step we do nothing. Whereas in the combine step, we do quite a lot of job. Remember that we learned the function named merge, right? So this is the function where we spend most of the time last week, and so this is the application of divide and conquer in merge sort. And now let's look at its application in quicksort. So in quicksort, what we do is this. Again, we're giving a very long. If we're giving a very long array, we say that okay, this is to merge. But what do we do is that okay, here we're going to pick the last value, the last element in the array in the array. We're going to take the last value in the array and give it a name called pivot. So what we do is that next we're going to divide the whole array into 3 parts. Instead of 2 parts, we're going to divide it into 3 parts. So the left part only includes values that are less than the pivot. So less than or equal to the pivot. So that okay. So and then the middle part. The middle part only it's the middle part is basically a subarray that only includes the pivot. So the middle array only the length of the middle array must be 1. So this is the pivot. We put a pivot in the middle, and then so in the in the third array or in the right subarray, we store all the values that are larger than the pivot. So the relationship between the first subarray and so the 3 subarrays are like this. So the middle subarray only includes the pivot, whereas the left subarray only includes values that are less than and equal to the pivot, whereas the right subarray only includes values that are larger than the pivot. So this.
So I'm a bit confused. Didn't you say the pivots was the largest number in the array?
No, it's just the last number in the array. We don't care about what kind of value it is. We just pick the last value.
It's always the last number in the array?
Yes, it's always in the last of the array, at the last position of the array.
Okay, thank you.
No problem. Okay, any other question? Okay, so here you can see that. So so this is just a one divide step, one step of divide. And okay, here let me say, if all the values, so for the pivot, okay, after this step, if all the values before the pivot are less than or equal to it, and all the values that are larger than it are behind it, okay, so can we say that the pivot is at the correct place in the array? I mean, in the.
Yeah, would be.
Yes.
Yes.
Yeah.
Okay. Yes, it's in its correct place, right?
Yes.
If all the values
Correct,
before are less
Yeah, it
than.
would be the mean.
Median.
We always
Not exactly the median.
position, right?
Not exactly the median. So it's possible. So here, let me draw the example in another way to make it a little bit clear. Okay, so it is very possible that we got the two left and the right subarray very unbalanced.
Oh wait, I see now. Okay, yeah, it won't be the median. It could be, but it's not likely.
Yes. So it's possible that, so if the last value in the input array is very small in the whole list, in the whole array, then we probably can get into a situation like this, where the left subarray only includes a few numbers and the right subarray includes a lot of values.
Could it also be possible for the pivot to be the largest or smallest number and then have nothing
Yes.
before or after that?
Yes. So if by some luck the pivot is the largest, is the smallest value, then the left array is basically going to be empty because no value is going to be smaller than it. So there is nothing, no element should go into the left subarray.
Would it still create a left subarray even though it doesn't have any value?
Yes, we imagine that we created it, but so it just does not exist.
Oh, okay.
Yes.
There's like an array that just doesn't have any numbers in it.
Right.
Okay.
It's basically empty. Okay. So, any other question? Okay. So and then I'm going to continue explaining the divide step, okay, of the quicksort. And so after that, okay, so we know that the pivot must be in its correct place already. So so we don't need to worry about it anymore. Instead, let's worry about the left and the right subarray, because it is possible, it is very possible that the values in the left and the right subarray are not sorted. So we only guarantee that all the values here are smaller than the pivot, but it's possible, it's very likely that these values are not sorted. So in order to get these values sorted, what we do is like this. Again, we are going to follow the previous step to divide it. So we're going to pick the last value from it and call it a pivot, and then we're going to divide it into three parts: left, right, and the pivot. So we got the pivot in the middle, right? And they satisfy this relationship. Okay, so we are going to perform another divide step at the left subarray and result in a situation like this, where we got left, middle, and right. Whereas the left only includes values that are less than or equal to this new pivot, this blue pivot. Whereas the right subarray only includes value from this subarray that are larger than the pivot. And similarly, we're going to perform the same operation at the right subarray over here. We're going to take the last value as the pivot, and then we're going to divide it into three parts. So okay, and here the less than and equal to, this relationship still satisfies. From this subarray, all the values that are smaller than and equal to the pivot are going to the left subarray. And so among here, all the values that are larger than the pivot are going to reside in the right subarray. Okay, so and this is I'm just going to copy and paste the original pivot over here. And this relationship still satisfies. So I just copy this less than and equal to sign from here, okay? And then I'm just going to copy this less than sign from here, okay? So basically we got quite a few subarrays with this relationship, whereas some of them only includes one number. Okay, so what we do is that as long as we see a subarray whose length is larger than 1, we're going to keep the dividing steps over it until all the subarrays are of length 1. So here we just execute a lot of divide steps for those subarrays that includes more than 1 value. And after that, we are going to be able to say such a situation. Okay, so we're going to enter such to go into such a stage where so we got a lot of subarrays, and each subarray only includes 1 number, and this subarray satisfies this relationship. So the first subarray is less than, and all the values in the first subarray is less than and equal to the second one, and the second one is less than and equal to the third one. Okay, because each of them only includes 1 number. So basically, we got all the numbers sorted. Is that clear? Any question?
Yeah.
What's
the formula for Quicksort?
There is no formula. I mean, do you mean the pseudocode?
No. So like how merge sort is
Oh,
and log
the
n.
complexity part, right?
Mm-hmm. How long it takes?
I'll give the conclusion later. For now, I just want everybody to focus on the understanding of it.
Okay.
So is it right to say that that Quicksort sorts itself as it divides, and then merge sort like it divides itself first and then it compares it when it combines?
Okay, so here what we can say is that in the Quicksort, so we do all of the tasks in the divide step, because at the end of the divide step, all the values have already been sorted. So there is no need for us to do conquer and combine.
Yeah.
Okay. So any other question? No? Okay, actually, I think I can use a better example to explain the big picture of Quicksort. So that is here. Okay, suppose here in our classroom, we have a couple of students. We have quite a few students. Let's say we have A and B, C, D, E, and we have, let's say we have F. Okay, so so what we want to do is that, so next what we want to do is that, okay, I'm going to make their height a little bit different so that it's easier to see. Okay, so suppose here we got 6 students in our classroom, and my objective is to get all the students sorted based on the height from the shortest to the highest. Okay, so this is my objective, and so if I use Quicksort, so the steps would be as following. Okay, so first I'm going to pick say a pivot, which is F. So this one is going to be the pivot that this student is going to be the first pivot that we pick. So okay, so we're going to pick the last student as the pivot, and we're going to arrange the students in the classroom, use some magic to divide the students in our classroom into 3 groups. So where the first group only includes students that are shorter than the pivot. So let's say here we got the first group with A, C, and D. They are shorter than our pivot F. So this is the first group. We have the group 1. And then we got the second group, which only includes the pivot. So this is F, our pivot. I'm just going to use the pink color to denote this is the pivot. And then so we got the third group, the third group, which includes the student B and E, which are taller than the pivot. Okay, so this is the last group. Okay, so the third group that we got. So after we finish the first divide step, what we know is that okay, F, the student F is in its correct place already, because all the students before it are shorter than him, and all the students after it after him are higher than him. So he's in the correct place, right?
Yes.
Okay, so it is in the correct place. And the next, by following the so we just finished one divide step, and the next, look at here. Okay, what we do is that for those groups, for those groups whose length are longer than 1, we are going to keep dividing them. Okay, so here we got a group, this group whose length is 3, so we're going to keep dividing it. And the way for us to divide this step is that we're going to take this student as the pivot, D, the last one from this group, as the pivot, and then we're going to divide this group into 3 parts, where we got so the first group that only includes students that are shorter than the pivot, and then the second group is D, and the third group is A. So now each of them is in, so here we got 3 groups. Each of them only includes one student. So we don't need to worry about any of them, because each of them is in the correct place. And then next, so this is the I'm going to copy the F from the previous step. Okay, so this is F. Okay, next let's look at this group. This group, the size of this group is 2, so we need to worry about it, and we are going to divide it, take the last element of this group as the pivot. So this is the pivot. Okay, so E is the pivot, and then we're going to divide this group into three parts, where the first part only includes values, students that are shorter than E. So here so the first group only includes 1 student, no worries. And then it is E, and after E there is nothing. This is basically empty, empty, because no student is higher than E. So the third group is going to be totally empty. So here, after that, we find that we are in a stage where we got 6 groups or 6 subarrays, and each of them only includes 1 value, one student. And so we end up with we finish the divide step, and here we can see that we got them sorted based on the height. That clear?
Yes.
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 Professor, I have a question.
Sure.
So like in this quicksort algorithm, we know that like let's say the example you gave now, that was pretty like 6 elements in the array. I mean 5. But well, like how, let's say if you have an array with like hundreds of elements, then on what basis would you choose your pivot then? I mean, you can't just select.
Just the last one.
Just yeah.
Yes, it's always the last one.
So for any size array also?
Yes.
Okay.
So suppose that no matter it is the whole array or just a portion of the array that so you are given to divide, you always pick the last one from that portion.
Okay. All right. Thank you.
No problem. So, any other question? Any other question? Okay. So, if no, so I'm going to enter to talk about the details about Quicksort. And so here I just want to give you the big picture about it. So and then here is what I just said. In merge sort, we apply divide and conquer, and most of the work are done in the combine step. Whereas in Quicksort, we do most of the work in the divide step. Actually, all of the work in the divide step, because when we finish divide, there's nothing, no more thing to do. So And so this is the pseudocode of Quicksort. So Quicksort is like, in Quicksort, there are two functions. The first one is named Quicksort, and the second one is named partition. So the partition function really helps us to do the divide. Okay, this helps us with divide. So we're going to spend more time on the partition function. And so let's look at the pseudocode, okay? Here we got the partition function, which takes 3 input arguments, A, P, R. So A is the array, we all know it. What does P and R stand for?
Starting and ending index.
Yes, awesome. Yes, starting and ending index. This is what we learned from the merge function, right? Sorry, the merge sort function. In merge sort. So we got 3 merge sort in the merge function. We got 3 input parameters, which are
PQR.
PQR. So P is the beginning index of the first left array. Q is the end index of the left array, and R is the end index of the second array or the right array. So here, great. We got P and R. So P and R. So the purpose of P and R is like this. Okay. So suppose here you are giving such an array. So now your task is to divide this subarray. Okay. Your task is to divide this subarray. So naturally, you will ask a question: what is the location of this subarray? So then you'll be given 2 values, which are the beginning and index of it. So the beginning and index of this subarray, P and R. So that's why we got so P and R over here. So P is the beginning index.
Is P and R usually the variables assigned for the first and last index?
Not actually. So usually in the programming world, the convention is to use IJK. So variables like IJK for the index, or for the to denote the number of iterations. But so for PQR, there is no so widely accepted convention on what kind of values should we use them for. So I guess the reason is that when you are going to a software engineering company, so you are not going to spend you're only going to spend a very small fraction of your time on arrays. Instead, you are going to spend your time on more advanced data structure. So R is the ending index. So okay, and let's look at the pseudocode. So first we have x equal to AR and I equal to P minus 1. So then we have a for loop and a if statement. And we have 2 exchanges: exchange something with something and exchange something with something. And then we finally return I plus 1. So let's write the, let's go through again, we're going to go through the pseudocode with an example. So I'm going to write down the pseudocode on the left. Okay, so this is the pseudocode, and I'm going to use an example to go over it. Okay, so I can sorry, I can remember I can memorize the pseudocode, but I cannot memorize the example. So I need to go to the next slide to get the values. So 28713. And then we got 3564. Okay, so this is so here. This is the array that we're giving. Suppose that so this is just the whole array that we're giving, and the index of them are starting from 1 to 8. So and our task so here our task is to divide this whole array into 3 parts. And so in that, so we will need to call the partition function over it. So so then what kind of values are you going to give to P and R?
P would be index 1,
Mhm.
and R would be index, I think A is the last one.
Yes, correct. So because P and R are the beginning and ending index, so in this, so if we want to say divide this whole array into 3 parts, then we need to so set P as the beginning index and R as the end index. So that's why we got a P equal to 1 and R equal to 8. Okay, so and for the so here I'm going to write P over here and R right over here to denote the location. Okay, cool. So next we have X. So we're going to execute the first line. We have X equal to AR. X equal to AR. So what is AR here?
It's 4.
4. Yeah.
Yes. So it is the value that is pointed by R, and it is 4. So so here we have X equal to 4. So here, if we go back to the explanation over here, so what is R base? So sorry, what is basically X?
It's the
X is your
pivot.
pivot. Yeah.
Yes, the pivot. So X is just the pivot. Okay, so I'm going to write down the value of X right over here. And next we have I equal to P minus 1. So what is I?
Isn't it the index before the first one?
Yes, it's the
Isn't
index
that
before the first
empty?
one. Yes, because P is 1, because since P is 1, so I is the initial value of I is going to be 0, right?
Mhm.
So it's like so I is the index that just right before the start of the array. So we are going to put I over here, which points to 0. Okay, so
When we're writing code, it'll be -1, right?
yes, correct. Okay, so next we have this for J starting from P to R minus 1. So the initial value of so here we have P as 1 and R as 8. So the ending value of J is 7. Okay, so for J starting from 1 to 7, so initially we have J as 1. Okay, J is 1. So I'm going to write J right over here to denote the location that it points to. So J is 1. Okay, so here let's say if AI if AJ is I forgot an equal. Okay, so if AJ is less than and or equal to X, we do something. So what is AJ now?
Isn't it 2?
Yes, AJ is 2. this is here is j, so aj is just pointed by j, so it is 2. So what about x?
If 2 is less
It's
than 4.
4.
4. Okay, so here we can say that this is true, right?
Yes.
So
Yeah.
so this is true, and then we're able to execute the next two statements with I++ and exchange AI and AJ. So first we're going to increase I by 1. So I goes from, so originally we have I as 0. So next we're going to increase I by 1. So I is going to be 1. And we're going to move I from here to the same position as J, to over here, okay? So, and next we are going to execute this line so in which we're going to exchange AI and AJ. So here, because both I and J are 1, so this would be exchange A1 and A1, right?
Yes.
So it's like I ask student A to exchange the position with student A. So that student is going to remain unchanged in its place, right?
Yes.
Okay. So this is something like I ask you to exchange. I ask you to exchange your house with your house. So you still owns your house, and so same here. We're asked to exchange AI with AJ. So nothing changes in the array. Okay, that's fine. So then we just until here. So okay. So let me just propose two statements. So or two statements. So the first statement is that in the subarray from P, the subarray starting from P to I. In the subarray from P to I, all the values are going to be less than and equal to X, which is the P word, and all the values starting from I plus 1 until J is going to be larger than the P word. Okay, so let's say at the end of this so after we just finish the exchange, is this true or false? Okay, so here I'm just going to use a different color for the second one. I'm going to use maybe so dark green color. Okay, I plus 1 until J is larger than X. So okay, so the first subarray that we talk about starts from P and ends at I. So here I'm just going to mark it with the same color. From P ends at I, so it's here. This is the subarray that we talk about. From P and ends at I, so this subarray now only includes one element, which is this value. So is this value less than X for the P word?
Yes.
Okay.
Yeah.
Yes. So this is true. And then let's check the second condition, or the second statement. All the values from I whose index are starting from I plus 1 until J are larger than X. So we have I plus 1 here and J, we have I here and J here. So I plus 1 is like all the, so over here is something like all the values from A2 until A1. So basically the end index of the subarray is larger than the beginning index of the subarray. It means that there is nothing in the subarray, right?
Yes.
It means that this subarray is empty. So then automatically this one it still holds. This one holds because nothing is in the array, so it holds. Okay, and nothing is in the in this subarray. So this statement holds. Okay, so here we just finished the if statement. Sorry, we just finished the exchange line. So where should we go next?
We're basically now checking the right side. So
The right side?
Go back to the for loop.
Yes,
Oh yeah,
we should.
yeah, go back. You're right. We didn't finish the
Yeah,
for
we
loop.
should go back to the for loop. Yes, correct. This is a trap. We just finished the if statement, and which is a part of the for loop. So we should go back to the for loop. And when we go back to the for loop, we should increase j by 1. So j now has a value 2. Now j has a value 2. Okay, so we're going to move j over here. Okay, so now what is aj?
8.
8. Okay, so in this, so x remains the same. So this is going to be false, right?
Yes.
Yeah.
Very false.
And so we will not be able to execute the next two statements. So, but again, at the end of the for loop, at the end of this iteration, so let's check if these two conditions are satisfied. Are all the values from p to I, so in the array less than x? So this is p and this is I. So the left subarray only includes one value, which is 2, and this value is less than x, right?
Mm-hmm.
So then let's check the second condition. So the subarray starting from I plus 1 until j. So I is here and j is here. So I plus 1. So starting from I plus 1 until j is basically the subarray over here. It only includes one value, and it's also larger. So it is larger than x. So these two statements are true, right?
Mm-hmm.
Okay. So next, let's so we just finished one iteration of the for loop, and we go back to the for loop, and we're going to increase j by 1. So j becomes 3.
It's going to do the same thing.
Yes, we're just going to keep to do the same thing. Okay. So then what is aj?
7.
7. Okay, aj is 7. So here we're going to give it a new value 7. Is this true or false?
False.
It's false, so we're not going to do anything. But let's check if this condition is true or false. So here, when we are executing this iteration, I remains unchanged and p remains unchanged. So this previously if it holds, so now it still holds. Then we only need to worry about the second statement because we just increased j by 1. So now, so let's check the subarray starting from I plus 1 until j. So I is here, j is here. So the subarray starting from I plus 1 until j is basically, I'm going to write j over here, and this is I plus 1, okay? Starting from I plus 1 until j is basically here, this subarray. So are all the values in this subarray larger than x?
Yes.
Okay, cool. So this still holds. And then we go back to the for loop, and then we're going to increase j by 1, so j becomes 4. So j becomes 4. Okay, so what is aj?
1.
Yes, aj is 1. So, and then this is
The
true.
condition is true. Yeah.
Yes, this condition is true. So we're going to execute I plus plus. So we increase I by 1, and then the new value of I is 2. So we are going to move I to 2, okay? And then we're going to exchange AI and AJ. So AI is basically A2, and AJ is basically A4. So we are going to exchange A2 with A4. We're going to exchange these two values. Okay, so after they exchange, they become 1 and 8. Right? Am I correct?
Yes.
Yeah.
Okay.
What's bothering me right now is that, so the way you explained the theory of the code before looking at the pseudocode, 8 was supposed to be before 7, but now it's after the 7.
Sorry?
So like the 8 was supposed to be like I understand the pseudocode the way it's working right now. It's 2178, right? But
Yes.
when you were using your analogies earlier, isn't the 8 supposed to be before the 7?
Which one is supposed to be 7? Sorry, I don't get
So
you.
the A4, so
Okay.
the 8, the in index 4, shouldn't it be before the 7? No, I
Before
understand the
7?
code.
No, it shouldn't be. It shouldn't be. So because so far I'm still following. I'm following the code exactly, right? So we're just we're just exchanging A2 with A4,
Okay.
correct?
Yeah.
So originally it was 2871. So now it becomes 2178.
Mm-hmm.
Okay. So so here, okay, we just did this exchange, and after this exchange, let's check if these two conditions are true and false. So the subarray starting from P to I, so because we just increase I by 1, so the left subarray size increases by 1. So it is like this. And so, but still here we can see all the values are less than X, which is 4. And then, so the right subarray starts from I plus 1 until J, so which is over here from I plus 1 until J. So it also includes two values. All of them are larger than X. So this condition is still true, okay? And then we just finished the exchange line, and then we will go back to the for loop. And so we are going to increase J by 1, and J becomes 5. Okay, so J becomes 5, and so what is AJ?
3.
3. So is this true or false?
True.
True. Okay, this is true. So we are able to execute I plus plus. So so then we increase I by 1. Okay, and exchange AI and AJ. So here, because I is, so let's just look at the picture over here. So this is I and this is J. So we're going to exchange these two values, right? These two values, 3 and 7, right?
Mm-hmm.
So we're going to exchange them, so they become 3 and 7 after the exchange. Okay, so and then we just finished this line, and so before we go back to the for loop, let's check this if these two conditions are true or false. So because we just increased I, so the pink array size actually increased by 1. So but still all the values here are 2, 3, 1. So it includes the value of 2, 3, 1, which are less than and equal to X, which is the pivot. Whereas the right subarray, so it starts from I plus 1 until J, it is still larger than X. Okay, so then we go back to the for loop again. So we increase J by 1, so J becomes 6. So what is AJ now?
5.
So J is AJ is 5. Okay, I should use a different color. So AJ is 5, and so this is going to be false.
Mm-hmm.
So we're not going to do anything in that round, and so in this iteration we're not going to do anything. But here, since J, we increase J by 1, but it keeps I unchanged. So let's say here the right subarray got expanded by so the right subarray size actually increased by 1 because we just increased J by 1. Okay, so and here you can see that all the values are larger than the pivot at X. Okay, so this is still true, and then we go back to the for loop and have another iteration. So we increase J by 1. So J becomes 7, and J becomes 7, and So what is AJ now?
6.
6.
Yes, AJ is 6. So here it is still false. Again, it is false. So we're not going to do anything. But so since we just increased the J by 1, and what we can say is that the right subarray got expanded by 1 element. But still, all of the values are larger than the pivot X. Okay. So then we just finished this iteration. So then should we go back to the for loop again?
No, because
No.
you ended it R minus
Yes.
1.
Yes, because J currently J is 7. It already reaches its maximum value.
Oh yeah. Oh, you have to iterate once more.
Yes. So then we should stop over here, right? Stop the whole for loop just terminates over here. Correct?
Mm-hmm.
Okay. So then, so here let's say at the end of the for loop, what we get in the array is this. Okay. So the left part are the values that are smaller than or and equal to the smaller than or equal to the x smaller than or equal to x, which is the pivot, and the right so the middle part is a subarray that is larger than the pivot. Okay, the following that is the pivot. Okay, so basically we got an array like this. We divide the array into 3 parts, which are like so this is the pivot X, and this part is larger than X, and this part is less than and equal to X. Am I correct?
Yes.
Like what we got over here, okay? Because all these conditions remain true, okay? So but remember, what we want to get is something like this. What we want to get is something like this. We want to put the pivot in the middle, whereas the left part are the values that are less than the pivot, and the right part are the values that are larger than the pivot. So this is what we want to get. So I'm going to write down what we want to get. Over here, we want to get something like this, less than or equal to X, and this is X, and this part is going to be larger than X. So this is what we want to reach, okay? But so far we are just at here, right? So we need to go from here to over here, okay? So if you are only allowed to, so here if you are asked to come up with a minimum change to go from this situation to this situation. So what kind of things can you think about? What is your idea to go from here, this stage, to this stage?
I mean, it's in the code, Euro. Exchange AI plus
Yes.
1 in R.
So basically, if you exchange, if you just pick the first element in a middle array and exchange it with the pivot, so you will be able to reach this step, right?
Yes.
Okay. So and the index of this value is just I plus 1 because I is the end. So the I is the end of this. Of the left subarray P, this is Pi, and then I plus 1, and this is R minus 1, and this is R. These are the index. So here what we need to do is that we just need to exchange AR with AI plus 1. Got it?
Yes.
Okay, so that's why we exchange them. So with this exchange in this example, what we do is that we exchange these 2 values. We're exchanging these 2 values, okay? So then, so we got this 4 and 8, and this is our pivot, okay? So this is our pivot, and finally, at last it will return I plus 1. So what does I plus 1 stand for?
The index after that.
Yes, the index of what?
4.
Of the pivot.
No.
Yes. So this is the pivot, the index of the pivot. So why does it return the index of the pivot? The reason is here. Okay, suppose we're just executing the so we are just at this step, and we finish it. We finish so the first divide step, and so this is the index. This is so. I'm going to remove these colors. Okay, so this is the pivot. So after this step, we were going to further divide the left and the right subarray, right?
Mm-hmm.
So here, what you definitely want to know is what is the, because you already know the beginning index of the left subarray and ending index of the right subarray. Okay, there are P and R, but you want to know the ending index of the left subarray and the beginning index of the right subarray, right?
Mm-hmm.
So if you are given the index of the pivot, let's say the pivot index is Q. If you are given the index of the pivot, so you can just directly know that the left subarray ends at index Q minus 1, and the right subarray starts with the index Q plus 1. So then you can further call the partition function, over the left and over the left and the right subarray to further divide them.
And so in this scenario, the next two pivots would be I minus 1 and R.
Sorry? Yes.
Well,
yes.
okay.
Yes. No. I mean, here
in your example up above, it would be Q minus 1.
If you return I plus 1, then the left subarray ends at is going to end at this, and at I, and the right subarray starts at I plus 2, because you are returning I plus 1, right?
Yeah, I plus 1 is the fourth index, right?
Yes.
Yeah, okay.
Yes. Okay, so this is the partition function, which helps us to do this step. And so here, I don't want to make a stop or ask for questions, because you need to remember this is the index of the pivot, and we are going to directly use it in the other function named quicksort. The quicksort function is pretty easy to understand. So A is the array, P is the beginning index, and R is the ending index. If P is less than R, what does that mean?
The first index is smaller than the last index?
Yes. So what does that mean? We talked about it last week.
I mean, it's always true.
No.
I mean, like the last index is always going to be bigger than the first index.
No, the last index is
index.
always larger than or equal to the first index. If we only have a single an array that only has one element, the beginning and ending index would be exactly the same, right?
Oh yes, yeah.
So if P is less than R, what does that mean? The subarray that we want
is bigger than 1.
Includes at least 2 elements, right? Because previously we said that if a subarray only includes 1 element, it means that we don't need to further divide that array anymore. So that single element in the subarray is already in the correct place. We don't need to do anything for it, right? So we learned this. We also learned this in the merge sort function, right?
Yes.
Okay. So here, if the subarray includes at least the 2 elements, that means that we need to there is a need for us to divide it. So first we divide it, and to get so we store the pivot index in Q. So then we know that the left array is going to start at the place is going to start at P and ends at Q minus 1. And the right subarray starts at Q plus 1 and ends at R. So we're going to sort or we're going to sort them again. So this is what we have over here. So if we return the pivot index as Q, and then next we are going to sort the left subarray and sort the right subarray. Okay. So does it make sense?
Yeah, that makes sense.
Okay. Any question?
It sorts the left subarray first and then the right subarray, right?
Yes. And
Yeah.
actually it does matter. So you can just exchange the line 3 and line 4. Doesn't matter.
So what I was wondering, I was wondering this with merge sort as well. If there's a function to quicksort, why are we partitioning everything in the first place? Is it just to make the execution time faster?
No, because here the quicksort function calls the partition function, and we are only going to sort those left and the right subarray after we finish the divide.
I see. Okay. Thank you.
Yeah, so this is again the divide and conquer design philosophy. So after we divide this, we're going to only sort a smaller subarray, right? Okay.
And the merge function did the same thing as well, calling the previous partition.
Yes.
Okay, I see. Thank you.
Any other question? No? So I really want to make sure that everybody is following me. So far at the current stage, we have 21 students. Okay, one left. So we only have 20 students in the class. So just type in 1 if you think that you follow me, you understand it. Okay, wonderful. Yes, thank you. So it means that I have at least most of you, and so yes, that's great. And so this is the explanation of the quicksort function. And actually, in terms of the complexity, quicksort, this is the complexity of quicksort. In the worst case, it is O n squared, the same as insertion sort. But in practice, this is the most efficient one.
Wait, efficient in terms of code? Or
No,
like
yeah,
time?
no, in terms of execution speed.
But the
Why would it-
complexity is, yeah, the complexity is same.
Okay, so here, okay, we see that the complexity is higher than O n log n, right?
Mm-hmm.
Which
Yeah.
is the merge sort, okay?
Uh-huh.
So this, I know that this sounds very strange, but let me say, okay, and so, but you need to remember, okay, the big O denotes this is the worst case, right? Okay, so let me give you one example. So suppose that we have 2 students, A and B. Each of them takes 3 classes, the same set of classes. I say the score, the grade that students A received are, let's say C, A minus, while B receives something like B plus. Sorry, B minus and B minus. So if we talk about the worst, the worst case or the worst grade of these students, the worst grade of these 2 students, which one is better? let's say Alice and Bob. Okay, we got
Probably
Alice and
Bob.
Bob.
Probably Bob.
No, yes. In the worst case, Bob wins, right?
Mm-hmm.
So, sorry, Bob, the worst grade from Bob
Worst
is
grade,
B
yeah.
minus. Yes, worst grade. But if we talk about the average grade or GPA, we see definitely Alice wins. This is because we say Alice has a lot of chance to do pretty good in the classes, whereas Bob's grade remains very closely to so stays very like so most of his grades are just like the worst case grade, right?
Yeah. Mm-hmm.
This is pretty much something the comparison between so the Quicksort and the this is Quicksort, and then this is merge sort. The worst case, in the worst case, merge sort is going to be faster than Quicksort because it has a lower worst case complexity. But on average, in most cases, Quicksort is faster.
Mm-hmm. Okay, now I get it.
Okay, so does it make sense?
Yeah.
Would Quicksort be about like, since it's O(n) squared, is it the same time as insertion sort?
I mean, the worst case performance, they are going to be very similar. But in most cases, it is even faster than merge sort.
Okay. I see. I just want to compare it to insertion sort. I see how it compares to
Okay.
merge.
Okay. So in practice, the execution speed. I'm just talking about the execution speed. It is like Quicksort is going to be better than is better than merge, and merge is way better than insertion. Okay, so that's why, like, this is the most important sorting algorithm. If you go to a job interview and if you are asked to implement a sorting algorithm, even though the job interviewer does not specify that you have to implement quick, you need to go to quick. You need to definitely implement Quicksort. Okay, make sense?
Yes.
Okay.
Yeah.
So if you want me to give you something like this in terms of the actually Quicksort has almost this so Quicksort is easier. So in terms of Quicksort, it's like it's easy. It's relatively easy to implement. It's definitely harder than insertion sort, but it is easier than merge, and it is faster. It is also faster than it's relatively easy to implement and it's fast. So this is pretty much like we have a car that is cheap and also it's fast. It handles pretty well. So that's why in the industry, most people go for it. Okay, can you think about a car that is both cheap and fast?
Dodge Challenger.
Dodge Challenger at like how much does it cost? 30,000?
Yeah, I mean a good model. Yeah, good trim level. Yeah, probably.
Okay. Yes. So yes, when you are considering buying cars, yes, probably you should go for cars like that, right?
I mean,
So
yeah, but the fuel economy and all that stuff.
yeah. I got you.
I mean, if you're rich, yeah.
Yeah. Okay. Yeah. So let's talk about that later. Okay. Let's talk about the car later. So okay. So here, coming back to Quicksort. Any question?
Well, this was actually not specifically this, but how long did you say that our insertion sort homework was supposed to run for? Was it 2 minutes in class?
I mean, again, it depends on the size of the input and what kind of hardware do you have. So, for example, I have a i7 CPU, and the speed is around 3.8 gigahertz. So it takes me to sort an array with 1 million numbers. It takes almost like 6 minutes. It depends on the size and also the hardware.
Okay, I just didn't recall what you said in class, the theoretical one. I know it differs from machine to machine.
Yeah. Okay. Any other question regarding Quicksort? Okay, so then let's take a break for 5 minutes and come back at 7. Okay.
Okay, thank you.
Good,
Thank
thank
you.
you.
Okay, so let's come back and so I'm going to start the second part of our and talk about the cunning sword. Okay, so but before that, I want to ask so a couple of questions for you. Okay, so far, so do you have any suggestion for me in terms of teaching? Like, is there something that I don't do good, or something that I can improve? Can you hear me?
Yeah, I mean, I haven't had any problem. You're pretty good, so all good
Yeah.
from me.
I got nothing. I'm following just fine.
Cool.
Yeah, I'm following just fine.
Okay. Okay, thank you. So okay, do I talk too fast, or I know that I have some accent, so do I talk too fast?
No, I mean, I understand everything, so I'm good.
Everything's fine.
Okay, good. So then the question is that in terms of teaching, do you think that the current style of teaching, of learning, even though the current style of remote learning is a kind of like equivalent, or it is, do you think it I mean, do so if you are asked to choose from remote learning like this, or to go back to campus and have face-to-face learning, which one do you prefer?
I mean, obviously face to face, but because of like the virus and stuff,
Yeah.
we're gonna settle for Zoom. But yeah, always face to face.
I prefer
Okay.
Zoom.
Sorry, I didn't quite hear you.
Sorry, was the question was if you prefer face-to-face or Zoom?
Yes, I mean, yes, pretty much like this. Yes, like, so for our class, do you prefer Zoom or prefer face-to-face?
Zoom, but it depends on everybody.
I just want, so let's make things easy. If you prefer Zoom like this, just type in 1. If you want to go to face-to-face, type to 2, and type 2. And if you think it doesn't matter, not matter, so type in 3.
I feel like it depends though. Like I did an in-person class last semester, and it was terrible because we had to sit outside and like sit 6 feet apart. I could barely hear anyone. So I prefer in person when it's normal, and like not COVID in person.
Yeah,
Oh.
me too.
Okay. So yes, okay, I see most of the, I would say 1, 2, 3, 4, 5, 6, 7, 8. I see 7 ones, meaning that 7 students prefer Zoom, and I see 1, 2, 3, and 4 face-to-face. Okay, so it's like so far we got 8 support Zoom and 4 support face-to-face. So I ask this question because I'm just thinking about when should we go back to face-to-face, because say I love the face-to-face interactions, and because I can see your faces, and in that case I can see your faces, and I know if you understand something or not. And but the thing is that at least in this semester, even if we go back to face-to-face, to go back to the classroom, so everyone has to wear a face mask. Um, so last semester, I taught face-to-face classes for 2 months. It was not that good. There are a couple of reasons. The first is that when I wear a face mask, I have to speak more loudly than usual to make sure that the students can hear me. So when I keep increasing my voice using that when I use that voice for 1 hour or 1.5 hours, I lost my voice. I basically lost my voice. So I have to kind of like rush in a lecture, and so that when my voice is okay, I got everything covered. That's one reason, and the second reason is that say last semester when I did face-to-face teaching, inside a whole class, maybe only 5 or 6 students came to the classroom, whereas the other just sit at home and have the Zoom. So I use Zoom to broadcast my in-class teaching, and the cameras, the web cameras. So when this is the, and I think this is the reason why I bought my iPad Pro for teaching, because if I write something down on a whiteboard and use the web camera, so to stream it, most of them are not visible. So for those students, if we go back to the classroom, for those students who do not come due to like either because of their health concerns or because the classroom limits. I think our classroom only allows 14 students to come. It's out of 30 students that we have. So only probably only a half of student each class, only half of the students can come, and then the other half stay at home. So for the people who stay home, you're not going to be able to see the whiteboard very clearly. That's the two reasons. But I agree that face-to-face is a better way to teaching. But under the current situation, so what I'm thinking about is that so probably we will have a couple of face-to-face teachings this semester, when the cases are done. But still, I would say most of our classes would be done via Zoom, to make sure that the students who cannot come to the classroom, either due to the classroom capacity limitation due to the COVID or due to health reasons, still they can receive quality education. Do you think this is fine?
Yeah.
Okay, so so this is the plan so far. I just discussed this plan with a couple of colleagues. And, this is the conclusion that we reach. So I want to share it with you. Okay, so next we are going to learn the last sorting algorithm named the counting sort. So this algorithm is not widely applied, but it's just very beautiful. So and it's not very difficult to implement, and it's really beautiful. So I want to share it with you. So far, the best sorting algorithm in terms of the worst case time complexity is merge sort with O(n) log n, right? So the question is, can we do better than O(n) log n? So what kind of complexities are better than O(n) log n?
O(n)?
O1,
Yes.
yeah.
O(n). So
And there's of course constant.
how about O log n? Yes, I see something like I heard something constant. That is beautiful. Okay, so constant meaning O(n). So we're going to talk about constant next class. So here the complexity is like this. Constant is the best, and then O log n is worse than, is longer than O(n), and then On is longer than O log n. So the best sorting algorithm that we can hope for is this, is O log n, because given an array of length n, at least we need to go to check each element and to say what is their value. Even though we don't do any value exchange, we need to check each, we need to check, inspect the value of each of them, and only by checking the value of each of them, so it is going to take on, it is going to take instructions. So the best search complexity that we can hope for is just On. Nothing can be better than. We cannot do O log n. We cannot do O1. So this is the best that we can hope for. And then next, we're going to learn the algorithm that can give us On complexity. Okay, so that is named, the algorithm that can give us the On complexity is named counting sort. And actually the complexity of counting sort is On plus K. So where N is, we all know what does N stand for, but what about K? So here, okay, in order for us to apply counting sort, there must be a limitation in the array. There is a limitation in the array. That is that each element must be an integer in the range from 0 to K. So basically K, what is K? K is the maximum value in the array. Okay, so when K is less than or equal to N, when K is less than or equal to N, the complexity is, so the complexity can, so we can just ignore K and only keep N. So in that case, we got On complexity. Okay, so let me repeat that. In order for us to, the limitation, okay, in order for us to be able to use counting sort, the array must be integers starting from, the array must only include integers from 0 to K. Okay, so this is the condition for us to apply so the counting sort. And so when K is less than or equal to N, we got On complexity. Make sense?
Yes.
Yes.
Okay, so and this is the reason why we don't apply counting sort a lot in practice, because first, a lot of times we don't get to sort integer arrays. Instead we got to set double arrays, and the other reason is that so if there is any negative value in the array, then we cannot apply it. So it has a lot of limitations. And but again, as I said, the design of this algorithm is just beautiful. So let's look at the algorithm. So this is the pseudocode counting sort. It has 3 input parameters, A, B, K. So what does
Hello?
A stand for?
Oh, hello. I have a question.
Sure.
So like counting sort, is it like the same like sort library we get in like Java or Python? Like, you know, we get a sort function and we could, is it similar to this?
No, in Java provides the sort. Java provides the sorting algorithm for you by default, and it is Quicksort.
Okay.
And actually, in practice, almost all the I'm only I'm familiar with C++, Java, Python. All of them support the default sorting functions in all of them are Quicksort.
Okay, thank you.
Okay. So here, okay. So let's come back to the counting sort pseudocode. So it takes 3 input arguments A, B, K. So what does A stand for?
It's an array.
Yes, the array, the input array. What about B?
Is that also an array?
Yes, B is also an array. A is the input array to be sorted. So B is the output array. So previously we only learned something like we sort the numbers in place, meaning that if we're giving an array A, we just do some value exchange in the array A to get the values sorted. But here, this is what we did before. We call it in place sort. But here we are learning something called out of place sort. So which means that we are giving our array A, we do not arrange the values in the original space. Instead, we create another array B, and we just copy and paste the values from A to B. So only B is sorted at the end. Got it?
Yes.
Okay. So B is the output array, and actually it is of the same size as A. And what is K?
Integer.
I'm integer.
Yes, the maximum value. Great, the max value in A. So it tells you because the values in the array A, so must be in a range from 0, must be integers from 0 to K. So then K is basically the maximum value in the array A.
So to use this, to use counting sort, do we already have to know the max value in A?
Yes.
Okay.
Okay. So so here let's look at the pseudocode. So first, we create C as a new array, and and then we have a for loop. We have another for loop. So first we set all the values in C as 0, and then we have another for loop. We add some values to the array C, and then we have another for loop, and then another for loop. Okay, so let me explain this pseudocode now. So when I write down the pseudocode, I want you to keep thinking about, so what does each of these for loops do? So here we got 4 for loops. I want you to think about what does each of them do.
Is each array going inside another array?
No. Counting sort. Okay, so this is the pseudocode, and let's again play with an example. So the example that we want to play is this 22530. Two 2303. Okay, the index of the array A starts from here. So I'm going to create another array B that is originally empty and with 8 spaces of the same size as A. Okay, so here, suppose we want to apply counting sort. We want to apply counting sort over the input array A, and this is B. This is array B. So what kind of values should we use for A? For K. What is the value of K?
Five?
K would be
Yes.
the, yeah.
K, remember, K is the maximum value in the array A. K is the maximum value in array A. Yes, maximum value in array A. So here in array A, the maximum value is 5. So we have K as 5. Okay, so and here, let's double check, are all the values in the array A starting from integers from 0 to K? Okay, all the values in the array A integers from 0 to K.
Yes, they all are.
Yes, so it means that the array A satisfies this condition. So then it means that we can apply the counting sort to sort it. Okay, so so first it will create a new array C. So what is the size of the array C?
It's 8.
8? No.
7?
What is the index of the array C? Starting from 0 and ending at
9.
K, right?
9, yeah.
No.
Wait, no, I'm sorry.
So it would
6.
be next to.
6, yes. K plus 1, right? Because
Wait,
this,
what? Why
the
is
index,
it?
Because K is 5. So whatever, and then you have to include 0.
Yeah, so yeah.
Okay.
yes, it is the size of the array C is 6, or in general it is K plus 1, because so unlike the other arrays that we studied in the textbook, so this array's index starts from 0. Okay, so pay attention to it when you are doing your homework. So here we are just going to create an array C whose size is 6. Okay, make sense?
I got it.
Yes.
Okay.
Cool. So next, for I starting from 0 to K, or let's say starting from 0 to 5, we assign 0 to it, okay, to the corresponding place of it. Okay, so initially when I is 0, when I is here, we assign 0 to it. So this becomes 0, right? Next, we increase I by 1. So then I becomes 1. So we assign 0 to C1. So this becomes 0. And then this becomes next one, we increase I by 1. So this becomes 0, etc., 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 until we set all the values in. We fill zeros. We fill in every place of the array C with 0. Am I correct?
Yes.
Okay, so if we want to summarize, what does this do? Just few zeros in C. Okay, so next, so far, can anybody come up with what does the second for loop do? Think about it. I'm just going to give you 1 minute to think about it. What do we do in the second for loop? If you I ask you to use 1 sentence to summarize it. So what are you going to say? Okay, any idea on what we do in the second for loop? Okay, so if not, I'm going to go over it. Okay, so initially we have I, so initially we set j as 1, so, and this is like say a1 equal to say a1 plus 1, right? So what is what is a1? What is aj or a1?
2.
2.
2. Okay, so if we rewrite it, it becomes c2 equals c2 plus 1, right?
Mhm.
Okay, so we are going to go to C2 and add 1 to it, right? So
That is correct. Yeah, I think, yeah.
So are we just copying the values over?
Yes, great. We're just counting the values. So the reason why we add 1 to C2 is because we just say a 2. So we just say this value once. So we add 1 to it. The next time when we see 2, when we say a 2 in the array A, we're also going to increment this value by 1. Great. So let's continue. Next, we set j. We increase j to 2. Okay. So for we increase j to 2. Okay. So what is a2? We're going to apply substitute aj with this value. What is a2?
5.
5. So this becomes say 5 equals to say 5 plus 1, right? So we're going to add 1 to say 5. So originally it is 0 because we haven't seen any value we haven't checked any value in A. Now for the first time we see 5. So we increase the count for 5 by 1. Okay, next we're going to increase j by 1. So for starting from now, I'm not going to write down the index. So I'm just going to use my pencil to mark the place. So we increase j to 3. So what is a3?
3.
So we're going to increment the count for 3 by 1. So okay, so this value goes from 0 to 1. And next round we see a 0. So we're going to increase the count. We're going to increase C0 by 1, right?
Mm-hmm.
Okay, so this becomes 1.
So it's just counting how many times a number appears.
Yes. And next we see a 2. So we're just going to increase C2 by 1. We're going to go to C2 and increase it by 1. So this becomes 2. And next we see a 3. So we're going to increase C3 by 1. Okay, next, we see 0. We're going to increase C0 by 1. And next, we see 3. So we increase C3 by 1. Okay, so here you can see that so we just finished the second for loop, and what we do over here is that we just count how many times does each value show up. So this is the result. Let's double check it. How many times does 0 show up in the array A?
Twice.
2.
Twice. So that's why we have a 2 in C0. How many times does the value 1 show up?
Not
once.
0.
Yeah.
How many times does the value 2 show up?
2.
2. Yes. 3 shows 3 times. That's why we have C3 as 3. Okay? Make sense?
Yeah, now, yeah, I think I get it now.
That's actually really clever, like a clever way to sort it.
Yes. That's why I want to introduce this algorithm to you, because even though it's not widely used, I think the design behind it is really beautiful. Okay, so this is what we do in the second for loop, and we just counted the number of values, the number of values in the array A. So, any questions so far?
No.
Okay, so now before I explain the third for loop, can you think about what we do in the third for loop? Okay, 1 minute.
I think we're gonna sort it on the base of number of time it occurs. So, like, we see like 0 appears 2 times, so all the zeros would come first, something like that.
You can see something like that, but not exactly.
Okay. I mean, we know how many times it's gonna occur, so we're just gonna use that and then
yes, we're
sort
definitely
it.
going to use that, but we are not going to use that directly. Okay, so then I'm going to continue. Okay, so next we have another for loop. For I starting from 1 to k, say I equal to say I plus say I minus 1. So initially we have I as 1. So I is here, I as 1. So when I is 1, if we rewrite it, it is C1 equal to C1 plus C0, correct? So we're going to add C0 to C1. So now C1 goes from 0 to 2. Okay. So in the next iteration, we increase I by 1. So I'm going to skip the index over there. So this becomes, so I becomes 2. When I becomes 2, so we can rewrite this line as C2 equal to C2 plus C1, right? Am I correct?
Yes.
Yeah. Till now.
Okay. So what we do is that we add C1 to C2. So we add 2 to C2. Okay, so C2 goes from 2 to 4, right? And then in the next one, we increase I to 3. So this becomes C3 equals to C3 plus C3 equals to C3 plus C2. Okay, we are adding C2 to C3. So now you can see that in each iteration, we basically add the previous value to the value follows it. right?
Basically the sum of the array. We just add up the whole array, right?
Yes. So
Okay.
now this becomes 7. And then in the next one, what we do is that we add this 7 up to the next value, right? So the next value becomes 7 again. And so in the last iteration, when I reaches k, which is 5, so we are adding this 7, say 4 to say 5. So the last value in the array becomes 8.
Yeah.
Am I correct?
Yep.
Yes.
Mhm.
So what do these values stand for? Two, 2, 4, 7, 7, 8.
The difference in between each index.
No.
Like the sorted version of the sum of the array, like a.
No, because you can see some values like 8, and 8 does not appear in the original array at all.
Yeah, I mean, I don't know.
Okay, let me ask you a couple of questions, okay? In the array A, how many values are less than or equal to 0?
2.
2. How many values are less than or equal to 1?
2,
2.
How many values are less than or equal to 2?
4,
4.
How many values are less than or equal to 3?
7.
7.
These values just tell you how many values are less than or equal to the index.
I see.
Okay. All right. Mm-hmm.
Got it?
I see it now. Uh-huh.
Okay, any question?
Wait, so this is not the final step, right? And
No.
there's still
Yes,
more.
this,
Yeah.
we're just at here. We just finished here.
Okay. Uh-huh.
Okay, so there is one more. One more for us to go. Any question so far? Okay, if not, I'm going to continue. It's going to burn your brain next. So let me give you an example. If I tell you that, so again, I want to sort all the students in our class by the height. So there could be some students with the same height, okay? But if I say, okay, I found a student named Alice, and if I know that there are 8 students, including Alice, there are 8 students whose height are less than or equal to Alice. Okay, including Alice, there are 8 students whose height is less than or equal to Alice. Okay, if I know this, if I put Alice in the 8th place in our classroom, can we say that Alice is in its correct place, in his correct place?
Yeah, I get it.
Yes.
Mm-hmm.
Okay,
Based on height, yeah.
yes. If including Alice, or including Alice, if there are 8 students who are shorter than or have the same height as Alice. Let's put it in another way. Alice is the 8th shortest student in the class. Okay, if Alice is the 8th shortest student, so these 2 statements are basically equivalent to each other, right?
Yeah. Mm-hmm.
Okay, so if Alice is the 8th shortest student in the class, and then if I put Alice in the 8th place in a class, so can we say that Alice is at his correct place?
Yes.
Yes. Okay, same here. Okay, so so take that into the next for loop. So in the next for loop, we are going to have j equal to 1. So we have j over here, and So the next one is going to be really difficult. Okay, so BCAJ equal to AJ. So this is like, oh my God, I remember that when I learned this algorithm in my graduate school, my instructor basically couldn't teach. So I learned all these algorithms by myself. And when I learned this counting sort algorithm, and when I look at this line, I was like, oh my God, I shouldn't be here. BCAJ. So, but we will figure it out. So here, what is AJ? Let's be slow. What is AJ?
It's the original array.
Yes, it is 2, right?
Yep.
Mhm.
It is 2. AJ is 2. And so what about so here we know this is 2. This is 2. Okay, we are going to assign 2 to some place. So what about C2?
It's 4.
C2 is 4. Okay, we say a 2, we're going to see C2 is 4. Basically, C2 tells you that in the array, including 2, there are four values that are less than or equal to 2. Something like here, there are 8 students, including Alice. There are 8 students who are shorter than or equal to, or shorter than or have the same height as Alice. So where should we put Alice in that case? The 8th place.
Mhm.
So here, what we know is that from this array C, what we know is that including 2, there are 4 numbers that are less than or equal to 2. Okay, so where should we put 2?
In the 4th place.
The 4th place. So that's why if we transfer this, it will be B4 equals to 2. So we are assigning it over here because there are 4 values that are less than or equal to 2. So it's safe for us to put this 2 in the 4th place in a sorted array. Any question? Are you still with me?
Yes, I am.
Yes.
Okay.
Yeah. Mm-hmm.
Okay.
Be interesting.
So cool. So now this number is basically gone. We just put it in the correct place. It's like we move the student to the correct place already. And the next we are going to do this. Say AJ minus minus. So remember AJ is 2. So say AJ is basically C2 minus minus. So we are going to decrease this value by 1. This is because this value, this 2 is already gone. And in the remaining part of this array, only 3 values are less than or equal to 2. Okay?
So now it's going to add a 2 to the 3rd place.
Add 2 to the 3rd. Yes, the next 2 would go to the 3rd place if we say it. Okay? So next, so we just finished one iteration of the for loop. Next, we're going to increase j by 1. J goes here. And then we see, so we see AJ as 5. So then we go to C5. We go to C5, which is 8, which tells us that there are 8 values that are less than or equal to 5. So we should put 5 at the 8th place, right? It's just that we follow this line, right? If you see a value, go to the address book to check where should it go. It tells you it's 8. So you just put it at this place. And then next, you are going to decrease this value by 1 because this 5 is gone. So in the remaining part of the array, there are only 7 values that are less than or equal to the array, equal to 5. There can be at most 7. Okay, so next, we increase j by 1. So we say this value, 3. And then you go to the address book 7, it tells you 7. So you put this 3 at 7 over here. Sorry, we'll put 3 at the 7th place. And then you decrease it by 1. So it becomes, so instead of, sorry, I crossed the wrong value. So this becomes 6 and this becomes 7, okay? So this value is gone. And then next, we are going to see 0, okay? So you go to the address book, it tells you that 0 should go to the second place. So the, okay, you put it over here, and then this value is gone, and then you decrease it by 1. So next we see 2 in the array A. So then you go to the address book. It tells you that this 2 should go to the third place. Okay, so you put 2 at the third place. You cross it, and then you decrease this count by 1. And then next you see a 3. So the address book tells you that 3 should go to 6. So, and then this value is gone, and then you decrease its address by 1, so it becomes 5. And then next you come across a 0, so you go to the address book, which tells you that the 0 should go to the first place. And then this value is gone, you decrease the count by 1, it becomes 0. And then next you see 3, okay, you see a 3, and so you go to the address book, it tells you that it should go to 5 over here. So you put it over here, and then this value is gone. And then you decrease this count by 1. So at the end, so now you finish this for loop because J already reached the maximum value. And then, oh, sorry, this is not 1. So sorry, this is the 0 we got. It should go to the first place. So it should be 0, I'm sorry. Should be 0, okay? Yes, this should also be 0, okay? So okay, so here, this is the result array that we got. So are the values the same as the, does it include the same set of values as the array A?
Yes.
Yes, it does. Yeah.
Yes. So now we see all the values are sorted.
Such a funny algorithm.
Sorry?
That's an interesting algorithm.
Yes. Yes.
It's really clever. Like whoever
Yes.
came up with it, that's really clever, actually.
Yeah, it's pretty interesting.
I was wondering
Yes.
what's gonna happen to B after I saw C, but then yeah. Okay.
So basically, C is like the address for each value of A to go to. I mean, when I understand this algorithm, I was in such a huge joy. I spent almost a whole day just reading the book and trying to understand it. And when I think that I understand it, I was so happy. The design of this algorithm is just so clever. So any question for it?
Yeah, so I understand the logic behind it, but I get a little confused in the last 2 lines about how that works. I guess like I'm not used to seeing arrays within arrays, so that kind of threw me off a little.
Yeah.
Could you go into B bracket CA and CA J minus?
Sure. AJ. So AJ tells you which value do you see in the array A, right?
Mm-hmm.
So then C. So here we can replace AJ with the value. So CAJ, C of the value. C of the value basically tells you the address of the value.
Mm-hmm.
So then you just go to the array B and go to the address of the array, corresponding address of the array B, and put the value over there. Right?
Yeah.
Yeah. So this
Wait,
is
so you
what
go from A to C and then from C to B.
Yes, we first go to A, like over here. So if you see this line, so when we see 5, originally this value was 8, okay? As when we did the example, this value was 8. When we see 5, we go to the corresponding place of C to find the address of 5. So C5 tells us 8. So then we put a 5 in the 8th in the 8th address of B. This is what we did over here.
Okay, I see now. Thank you.
No problem. Okay. Any other question? No? So how do you like this algorithm?
I think it's unique.
I think out of everything we've learned, it's like the most beautiful code, just because of
Yes.
how, yeah.
Yeah, I agree. Yes, out of the 4 sorting algorithms, this one, the design is the most beautiful. So
Wait, you said in practice Quicksort, which was the quickest. It's the most practical one, right?
yes, Quicksort is the most. I mean, Quicksort is pretty general. There is no limitation on the input array, but instead, counting sort is a different story. And most of the time, this condition is not going to satisfy. So the maximum value in the array is usually much larger than the length of the array. So that's why in practice we cannot get ON complexity, and so that's why it's not. This is another reason why it cannot be applied widely in practice. So for example, if we have, so basically if we want to sort so other people in a town based on their age, then we can apply counting sort, because the maximum age, let's say, is 100, and then the population in a town can be easily as large as 20,000. So in that case, we can use counting sort. But in most cases, we cannot. Suppose that we want to sort the people in a town not based on the age, but based on their income. Then the maximum value, let's say, could be 1 million. But the town only if the town only has 20,000 people, so then the complexity is going to be way more higher than ON. Make sense?
Yeah.
So okay, so in your job interviews, just go to if you are asked to implement a sorting algorithm, just go for Quicksort without any hesitation. It's a safe choice. Okay, so next I want to briefly talk about the complexity inference. So here we are giving an algorithm, a pseudocode, and to infer the complexity of an algorithm, you only need to pay attention to 2 parts. The first part is the loops, and then the second part is the function call. Does this function call any other function? Function call. So here, in this algorithm, it does not call any other function. It just have loops. So when it only has loops, which we basically need to pay attention to the total number of iterations in the algorithm. So here we got a for loop. How many iterations are in the first for loop?
K plus 1.
Yes, k plus 1 in the first for loop. What about the second one?
K.
No, n, the size of the array.
Oh, sorry, I was looking at the third one.
Yes, the size of the array. How about the third one? Yes, you already said it. It's k. And what about the last one?
Array length.
Yes, the array length. So because these for loops, they are not nested, they're just parallel. So we just need to sum them up, and then we will be able to know the total number of iterations in this algorithm. So it will be 2k plus 2n plus 1. Okay, this number of iterations. And so here we got some variables like k and n. So if there is any variable in the number of iterations, we just eliminate the constant, because k and n can be as large as 1 million. When they are pretty large, these constant values can be totally ignored, and so they do not play a major part. So then we just ignore the constant, and then the rest of that is just the complexity. So that's how we reach the ON plus k complexity of counting sort. Make sense?
Yes, that makes sense.
Okay. So and we are going to learn more about the complexity inference in starting from next week. Okay. So here, so far we have learned 5 sorting algorithms, but here you can just cross the heap sort. It's not going to be widely. It's this one is not. It's not necessary for you to understand it. Okay. So we learned 4. So except for that, we learned 4 sorting algorithms: insertion, merge, quicksort, and counting sort. So quicksort is the best in practice, whereas merge sort and has the general algorithm. It's the general algorithm that has the least complexity, or worst case complexity. Whereas counting sort gives you the best complexity, but it comes with a strict limitation on the input array. So yes, that's pretty much what we need to discuss for the first section of our class, the sorting algorithms. Okay, so and after this class, you will have your homework 3. And in homework 3, I give you the object. So I'm just going to terminate the presentation from iPad and then start the presentation on my laptop. So here in homework 3, let me show you. So this is your homework 3. In homework 3, so you are given 4 tasks, but one of them is optional. The first task is to implement a quicksort. The second one is to implement counting sort, and the third one is going to be draw a plot, generate a report. So pretty much what you did in the first and second homework. And then, so for the first time, you got the opportunity to earn some extra credit, 100 points extra credit if you implement the heap sort algorithm. So I also provide you the skeleton code of heap sort algorithm in a separate file named sort4.java. So if you want to earn that extra credit and learn a very hard, a very complicated sorting algorithm, so this is the opportunity for you to do that. But I mean, be prepared. So this alone is like 8 hours. Okay.
Is it more difficult than counting sort?
More difficult. Counting sort is not difficult at all. Counting sort is difficult for us to understand, but it's in terms of the implementation, it's the easiest one. It's pretty much like, it's even a little bit easier than insertion sort. But in quicksort is something like merge sort. So okay. Any question for me?
It says 100 extra credit. Is that like, so it's like the worth just one homework then? Like one entire homework? Right?
Yes. It's like one extra homework.
Okay.
Yes.
Thank
That's
you.
a lot of extra credit for
Yes.
one task.
That's why I said, if you remember in the first lecture, I said that if you sum up, if you consider the extra credit opportunities, you can earn at most 120 or 22. So after this, there will be 3 more extra credit opportunities. I think 3. Yes.
Oh, someone wanted me to ask you this. Do you count attendance? Or do you check?
Attendance.
Yeah.
So far, I haven't like count attendance, but I probably will start doing that starting so from next class, because as you can say that so far we only have 17 students now, and I believe that my teaching deserves more.
Okay.
So
Mhm.
yes, so probably starting from next class, I will do the attendance.
I'll relay the info. Thanks.
Okay, thank you. And so I got one question from the chat earlier. What if you had a function inside the loop? You need to time that. So it's like you need to repeat that function for a certain amount of time. So suppose that the for loop is going to execute, let's say, 100 times or x times, and then the complexity of the function inside the for loop is y. So it's like x times y. So you need to multiply them.
So does it mean it turns quadratic?
Sorry?
So does it turn quadratic?
It depends. I mean, it depends. So this depends. I mean, if it depends on the number of iterations in the for loop and also the complexity of the function to be called. So if the complexity of the function to be called is O(n) squared, and then you need to call it n times, it is going to be n quadratic.
Okay.
Oh, sorry, not n quadratic. It's going to be cubic.
Okay.
Any other question for me? Okay. So then, if not, so this is our class for today. So I know that your brain must be burning, but hopefully it is worth it, and you think it's worth it. And so have a good night.
Thank you so much. Have a good night.
Good night,
Thank you.
everyone.
All right.
Good night.
Good night, Professor.
Good night, y'all.
Thank you.